Hey, this is Kyle, and I'm going to be talking about Homework 2, Part 2D, in which we're deriving Broyden's method as an iterative refinement of an approximate Jacobian. Alright, so basically, I'm trying to prove this equation is true, and that's a major key piece of Broyden's method when solving for the roots of a function. And we'll just do that by breaking down the components and basically deriving this function here. So a couple of the components we have in here, first we have, or when using Broyden's method, I guess we'll talk about that. As we iterate through Broyden's method, we're calculating a new function value until we reach a root. So we're calculating a new function value, so f n plus 1, and it's equal to f of n plus the Jacobian n plus 1 times delta x n plus 1. And delta x n plus 1 is x of n plus 1 minus x of n. And f of n plus 1 is the function at x of n plus 1, where f of n is the function at x of n. Just for ease of writing, I'm writing it like this. And this is while we iterate. And then once we actually reach the end of Broyden's method, we know we found a root to the function. So this f of n plus 1, this function is going to equal 0. So we found a root. So my computer just died, but it looks like it kept recording, or the OBS file kept on, so we'll just continue. Alright, so I think I was saying, when we finish Broyden's method and we find the root, we know that the new function value f n plus 1 is going to be equal to 0. And then it's the same formula, except it's just the Jacobian of n at n times delta x n plus 1, n plus 1. And this is at the end of Broyden's method. So what we can do is we can subtract these two equations, and what we're left with is f of n plus 1 equaling, the f of n's cancel since we're subtracting, equals j n plus 1. And by doing this, we're going to see that we have some like terms that we can combine and factor out, which I'll show in a second here. I'm just going to be writing delta x now, but delta x is delta x n plus 1, same thing, minus jn times delta x. So we can see that both terms have this delta x, so we can pull that out and have it equal jn plus 1 minus jn, both times delta x. And this equals f of n plus 1. So now we're going to introduce this vector u, and there's two cases in which we want to look at, and that's when our delta x and the dot product of u is equal to 0. And when this is true, it means that j of n plus 1 minus j of n times u equals 0. And it looks like I have a little room left if I move the paper up. And the second, like I said, this is case 1. And we have case 2. And case 2 is when delta x equals u. And in that case, we have j of n plus 1 minus j of n times u equaling fn plus 1. In each case, we have something times u equals 0, and something times u equals, or something times u equals another thing, something times u equals something. So Broyden's idea, basically what he's saying is f of n plus 1 times delta x transpose over delta x dot product delta x times this vector u is like a formula we can use. I wrote that down but off screen. So f of n plus 1 times delta x transpose over delta x dot product delta x times u is a relationship we can use to simplify some things. So let me go to a new page. This back down. Alright. So let me rewrite that. F n plus 1 delta x transpose over delta x dot product delta x times u. And we'll take a look at this thinking in terms of case 1, which is when delta x times u equals 0. So if delta x times u equals 0, that means that this delta x transpose times u is also going to equal 0. And if that equals 0, that this whole expression will equal to 0. And then if we look at case 2, which is when delta x equals u, and we take a look at the same expression, f of n plus 1 is delta x transpose over delta x dot product delta x u, and want to see what that's going to equal. So this u is equal to this delta x, so one of those will cancel. Then we have the transpose over the non-transpose of this delta x, and that's going to keep the identity of this fn plus 1 when you multiply. So this is equal to fn plus 1. And now as we wanted to test out this expression here, so something times u equals fn plus 1, something times u equals 0 when it's case 1 versus case 2. We can see that that something that we made is equivalent to this jn plus 1 minus j of n because it satisfies both conditions. So if that's equal to jn plus 1 minus jn, that means we can plug it in for that in its stead. So now what we have is we have jn plus 1 minus jn is equal to that proof we just did, f of n plus 1 times delta x transpose over delta x squared. And now if we take a look and compare this to the expression we're trying to prove, we can see that we have some stuff matching. So we have jn plus 1, jn plus 1. Then in this expression we have jn plus 1 minus j of n, but that's the same as jn plus 1 equaling j of n. Just if we subtracted j of n to the side, it would be the same. So those two terms are good. We have our delta x and our delta x, the identity, or the, that's squared. So we have that in both denominators, and we have our transpose multiplied into both fractions. So right now we're looking pretty good. The only thing we have left is that we want f of n plus 1. We want to show that that is equal to delta f of n plus 1 minus jn times delta x. So that's the last proof we need to make. So if I have this f of n plus 1, I want to show that it's equal to delta f of n plus 1 minus jn times delta x. So now the first thing we can do is delta f of n plus 1 is f of n plus 1 minus f of n. So we can do that replacement. And then we can come over here, and with this relationship we made earlier at the end of the Broyden's method, 0 equals f of n plus j of n, or sorry, f of fn plus jn times delta x. We can use that relationship, so if I'll rewrite that here, you can see 0 equals fn plus jn times delta x. Now, if we solve for jn, we can replace that here. So jn is going to equal, if we subtract f of n to this side, or fn to this side, we have negative fn, divide by x, and we plug in, so minus this jn term we have, which negative fn divided by delta x, that's our new jn, and then times this delta x that we carried down. So these will clearly cancel, and we're left with f of n plus 1 minus f of n, or fn, minus a negative fn, so this becomes plus fn, and we have minus fn plus fn, so this will cancel with that, and we are left with fn plus 1 equaling fn plus 1, and this is clearly a true statement. So that means that this thing we derived here, showing this is true, proves the equation, proves the formula we were trying to prove is correct, as this fn plus 1 term is equivalent to delta fn plus 1 minus jn delta x, so I can rewrite this using this proof that we just made. Yeah, close to the bottom of the screen, but it should be good. As jn plus 1 equaling, so I'm just putting this jn back onto the other side like the formula we wanted to prove is, jn plus, and now this is where I'll rewrite fn plus 1 as this term, so delta fn plus 1 minus Jacobian jn times delta x, and we'll bring back the n plus 1 here, over delta x n plus 1 identity squared times delta x n plus 1 transpose. And this, as you can see, is the same as the